Hello students, we are solving the IB Math A AGL past papers and currently we are solving the IB Math A AGL May 2021 paper 3 time zone 2 past paper, and we have already solved the question number 1 of this question paper, and today we will be solving the question number 2 of this paper. So, and you will be getting the links to all the previously solved questions of this paper and of the other papers in the form of playlists in the description area. So, without any further delay, let us start solving question number 2. The maximum mark is 24 and it says, this question asks you to investigate and prove a geometric property involving the roots of the equation z to the power of n equal to 1, where z belongs to the set of complex numbers for integers n and n is greater than or equal to 2. The roots of the equation z to the power of n equal to 1, where z belongs to the set of complex numbers, are 1 omega omega square, or you may read this as 1 w square dot 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 up to w to the power of n minus 1, because it is an equation of the nth degree, so there will be n roots and there are n roots. Okay, where w is e to the power of 2 pi I over n. Each root can be represented by a point p0, p1, p2 up to pn minus 1 respectively on an Argand diagram. They have given you the Argand diagram. I'll be coming to that Argand diagram very soon. Let us read the remaining statements before that. For example, the roots of the equation z square equal to 1, it is a quadratic equation where z belongs to the set of complex numbers, will be 1. Obviously, one of the roots will be 1 and the other is omega. On an Argand diagram, the root 1 can be represented by the point P0 and the omega. Root omega can be represented by a point P1. There are two roots and there will be two roots on the Argand diagram. Fine. Consider the case where n equal to 3. There will be three roots. The roots of the equation z to the power of 3 equal to 1, where z belongs to the set of complex numbers, will be 1 omega and omega square. On the following Argand diagram, the points P0, P1 and P2 lie on a circle of radius 1 unit circle, 1 unit, with center O having the coordinates 0, 0, the origin. Okay, let us get the diagram, the Argand diagram, where we are having the 3 points dotted P0, P1 and P2, which lie on the circle, unit circle. Okay, so this is the Argand diagram. This is the real axis. This is the imaginary axis. This is P0, the root will be 1 for this, and this is omega, and this is omega square. Okay, and this is the unit circle. So the subpart A, it contains two further subparts. The I says show that omega minus 1 times, or w minus 1 times w squared plus w plus 1 equal to w cube minus 1. We can just expand and we will be getting the right hand side. So let us do that. So A I equal to w minus 1 and w square plus w plus 1. Okay. If we expand this, what do we get? W to the power of 3 is multiplied with this gets multiplied with that, and this gets multiplied with this. Okay. So w to the power of 3 plus w square plus w. Again, this with this with this, and this with this. Okay. So minus W square minus W minus 1. These two cancel, these two cancel. So we have W cube minus 1. Shown. Okay. Coming to subpart I, hence deduce W square plus W plus 1 equal to 0. Okay. What was the equation? It was z to the power of 3 equal to 1. Yeah. And the roots were 1, omega, and omega square. Okay. So if we put omega in place of c, we may put, because the equation will be satisfied if we put 1 in place of z, or we put omega in place of z, or we put omega square in place of z, because these are the three roots of this equation. Okay. So if we put any of these three values, the equation will be satisfied. That means the left hand side should be equal to the right hand side. Okay. So we are putting W in place of Z. So let us just answer this over here. Since 1 omega or W and W square are the three roots of Z to the power of 3 equal to 1. Therefore, the left hand side will be equal to the right hand side of the equation if we substitute any of the three roots in place of Z. Okay. Left hand side equal to right hand side of the equation. This, okay, you understand the meaning. So therefore we substitute W in place of C. Okay. Therefore we get, it was Z to the power of 3 equal to 1. We are getting omega or W cube equal to 1. Z cube equal to 1 in place of Z cube equal to 1. Now we are having W cube equal to 1. So this gives us W cube minus 1 equal to 0. Okay. And over here, the right hand side of this equation is W cube minus W cubed minus 1, or W raised to the power of 3 minus 1. This is equal to 0. Okay. And W cubed minus 1 is equal to this portion. Okay. So now we come to over here. From I, we have W minus 1 times w square plus w plus 1 equal to w to the power of 3 minus 1, which is equal to 0. Okay? But since omega or w is not equal to 1, because these are the three roots of this equation c cube equal to 1, and one of the roots is equal to 1. Therefore, w or w square is definitely not equal to 1. Since w is not equal to 1, therefore w minus 1 is not equal to 0. So w square plus w plus 1 should be equal to 0. Okay? That is w square plus w plus 1 equal to 0. We have completed answering subpart A. Long way to go. There are so many subparts. So let us bring in subpart B. Line segments P0, P1, that is this one, and P0, P2, this one, are added to the argon diagram in part A and are shown in the following argon diagram. And P0, P1 is the length of this line, and P0, P2 is the length of this line. Subpart B says, show that P0, P1 times P0, P2 equal to 3. And let me just remind you, the equation was z to the power of 3 equal to 1. And it had the roots as 1 and omega or w and w square. And w was equal to e to the power of 2 pi I over n. In this case, n is equal to 3. Okay. So let us first of all write the coordinates of these points. This will be 1, 0 because this is on the real axis. The imaginary part will be equal to 0. One of the roots is 1, so it is 1, 0. And what will be the coordinates of the other 2 points? This one is omega. The P1 refers to omega. So what is omega? It is omega equal to e to the power of 2 pi I over 3, which is equal to, it is 1 times, it is a unit circle, so the modulus is 1 cos 2 pi by 3 plus I sine 2 pi by 3. Okay, so what is this equal to? Therefore, omega is equal to cos 2 pi by 3. Cos pi by 3 is half, but 2 pi by 3 is an angle from the second quadrant where cos is negative, so it will be negative half. Plus I sine pi by 3 is root 3 by 2, so sine 2 pi by 3 is root 3 by 2 I. Okay, so this will be negative half and root 3 over 2. Okay, and because this is the imaginary axis, this is the imaginary axis value, this is the real axis value. And for P2, that is omega square. So what is omega square? Omega square is omega times omega, or it is, okay, let me write it omega times omega, or w times w, if that is easier for you. I don't know which one will be easier. You can do whole square also. So it is e to the power of 2 pi I over 3 times e to the power of 2 pi I over 3. So it is e to the power of m times e to the power of m. The indices, the powers will get added. So it will be e to the power of 4 pi I over 3. Okay. So omega square will be equal to 1 cos 4 pi by 3 plus I sine 4 pi by 3, which is equal to, these two are from the third quadrant, right? So where both are negative. And from the diagram also, you can see it is in the third quadrant. So it will be negative half, negative root 3 over 2I. So this is negative half, negative root 3 over 2. Okay, now we have got the coordinates of the 3 points. We can very easily, you can use the vector method as well, but if students sometimes they are scared of vectors, so I'm just using the plain distance formula method to get the lengths of P0, P1 and P0, P2. Okay, so I'm doing it over here. So P0, P1 will be equal to under root 1 minus of minus half is plus half. So half whole square plus 0 minus root 3 over 2 whole square. Okay, so this is 1 plus 3 over 1 plus half is 1.5, that is 3 over 2. 3 over 2 whole square is 9 over 4. 9 over 4. And this one is minus root 3 over 2 whole square, which will be 3 over 4. So this is equal to 12 over 4, which is equal to root 3. Okay. Similarly, P0, P2 equal to 1 minus of minus half is plus half. So 1 plus half whole square plus 0 minus of minus 3, minus root 3 over 2. So it is plus root 3 over 2 whole square. Okay. So this is 3 over 2 whole square is 9 over 4 plus root 3 over 2 whole square is 3 over 4. So again it is 12 over 4. So this is also equal to root 3. Therefore, P0, P1 length times P0, P2 length equal to root 3 times root 3, which is equal to 3. Okay. Shown. So we have completed subpart B. Let us move on to the subpart C. Consider the case where n equal to 4. The roots of the equation z to the power of 4 equal to 1, where z belongs to the set of complex numbers, and the roots are 1 w square and w cube. So part C, by factorizing z to the power of 4 minus 1 or otherwise deduce that w cubed plus w squared plus w plus 1 equal to 0. It contains only 2 marks. Okay, fine. So z to the power of 4 equal to 1 means z to the power of 4 minus 1. You can factorize in different ways, but I'm using the algebraic identity a square minus b square. So this can be written as z square whole square minus 1 whole square. So this one is z square minus 1 and z square plus 1, which is of course equal to 0. And this is, let me now come to this point. Okay. So for z square minus 1, I am writing z minus 1 and z plus 1. And the other part is z squared plus 1. And I'll be combining these two, of course, because I need to get this. So this is equal to 0. So therefore, z minus 1, and I'm combining these two. Multiplication of two binomials, so it is z to the power of 3 plus 1 times z squared is z squared. Z times 1 is z, and 1 times 1 is 1, equal to 0. So we have got this factorized form and of the equation z to the power of 4 minus 1 equal to 0. And since the roots of this equation is, we are having 4 roots, 1 omega or w squared and w cubed, we may put w in place of z in this equation. If we put w in this place, in the place of z, let this be equation A. On substituting, w in place of z in equation A, we may substitute because w is one of the roots. Okay, so we get w minus 1 w cubed plus w squared plus w plus 1 equal to 0. Okay, and since w is not equal to 1, therefore w cubed plus w squared plus w plus w1 is equal to 0. Okay, so we have solved subpart C. Let us move on to subpart D. Okay, on the following Argand diagram, the points P0, P1, P2 and P3 lie on a circle of radius 1 unit. It is a unit circle with center 0, 0. This one. P0, P1, P0, P2 and P0, P3 are line segments. Subpart D says show that P0, P1 times P0, P2 times P0, P3, these are the lengths of these three lines, equal to 4. Again, we will be first of all finding the coordinates of these 4 points and we will be using the distance formula. Okay, and the equation is z to the power of 4 equal to 1. Therefore, the The roots are 1, omega, omega square, and omega cube. Okay, where omega is this? So, e to the power of 2 pi I over n. In this case, n is 4, so omega is equal to e to the power of 2 pi I over 4. N is 4, so this is e to the power of pi over 2 I. Okay, so we can find the coordinates of P1 refers to omega. So omega will be equal to, it is the modulus is 1 because it is the unit circle, 1 times cos pi by 2 plus I sin pi by 2. Cos pi by 2 is 0, therefore it is totally on the imaginary axis, doesn't have any real value, real part. Okay, and sin pi by 2 is 1, so it is just I. This one is, okay, let me first of all write this as 1 comma 0. This one is 0 comma I. And now omega square. Omega square will be omega times omega, which is e to the power of 2. Okay, let me write e to the power of pi by 2 I times e to the power of pi by 2 I. So pi by 2 plus pi by 2 is pi. So this is e to the power of pi I, which is equal to 1 times cos pi plus I sin pi, and cos pi is negative 1 and sin pi is 0. So this is equal to negative 1. So this one is negative 1 comma 0. Omega 3. I'm not writing the omega 3. You will be getting this as 0 and negative pi. Okay, you can do it. By symmetry also you are seeing it will be 0 and negative I. So now that we have got all the coordinates of all the points, we are in a position to get the lengths. First of all, let us get the length of P0, P1. Is equal to 1 minus 0, or this is not I, this is 1 rather. This is 1 and this is minus 1. Because the imaginary axis represents the I part. Okay. So this is 1 minus 0 whole square plus 0 minus 1 whole square. Okay. Equal to 1 plus 1 is root 2. P0, P2 is equal to 1 minus minus 1, that is 1 plus 1 whole square plus 0 minus 0 whole square. 1 plus 1 is 1 plus 1 is 2, 2 squared is 4. Square root of 4 is 2. Okay. Let us get P0, P3. This is equal to 1 minus 0 whole square plus 0 minus minus 1 is plus 1 whole square. 1 square is 1 and this is also 1 square 1, so root 2. Okay. Therefore, P0 P1 times P0 P2 times P0 P3 equal to root 2 times 2 times root 2 equal to root 2 times root 2 is 2 and times 2 is 4. Okay, shown. Subpart E. For the case where n equal to 5, the equation z to the power of 5 equal to 1, where z belongs to the set of complex numbers, has roots 1, w, w squared, w cubed, and w to the power of 4. It can be shown that P0 P1 times P0 P2 times P0 P3 times P0 P4 equal to 5. We will be plotting the 4 roots, rather the 5 roots on the Argand diagram. We'll be getting the lengths of those, and we will be multiplying, and we will be getting the answer as the product as 5. Okay. Now consider the general case for integer values of n, where n is greater than or equal to 2. The roots of the equation z to the power of n equal to 1, where z belongs to the set of complex numbers, are 1, w, w square, and so on up to w to the power of n minus 1, because there will be n roots. On an Argand diagram, these roots can be represented by the points P0, P0, P1, P2, and so on up to Pn minus 1 respectively, where these are the line segments. The roots lie on a circle of radius 1 unit, the unit circle with center 0, 0, the origin. Subpart E says suggest a value for P0 P1 times P0 P2 times dot 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 times P0 Pn minus 1. We have seen when the equation was z to the power of 3 equal to 1, the product was 3. When the equation was z to the power of 4 equal to 1, the product was 4. This z to the power of 5 equal to 1, they are saying the product will be 5. So when the equation is z to the power of n equal to 1, the product will be, of course, equal to n. It contains just a single mark, justified. Okay. P0, P1 can be expressed as this is the vector path, but don't get scared, don't get frightened. P0 will be referring to, it is on the positive side of the real axis. It is referring to the root 1, and P1 is referring to the root omega, so, or W. So it is written as modulus of 1 minus W. And subpart F says, it contains further two subparts. I says, write down the expressions for P0, P2 and P0, P3 in terms of W. So it will be I, P0, P2. P2 will be referring to omega square or W square. P3 will be referring to W cube. So this is P0, P2 will be 1, this is the absolute value, 1 minus W square, and P0, P3 will be absolute value of 1 minus W cube. Okay, fine. And subpart I says, hence find, so I over here, hence write down an expression for P0 Pn minus 1 in terms of n and W. So when P0 P1, it is 1 minus W, P0 is 1 and P1 is W. So P2 is W squared, P3 is W cubed. So Pn minus 1 will definitely be W raised to the power of whatever is the subscript that is becoming the power. So it will be w to the power of n minus 1. Okay. So this is modulus of 1 minus w raised to the power of n minus 1. Clear? So these are the answers. For subpart F, moving on to the last subpart G. Consider z to the power of n minus 1 equal to z minus 1 times z to the power of n minus 1 plus z to the power of n minus 2 plus dot 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 plus z plus 1, where z belongs to the set of complex numbers, and the last subpart I says express z to the power of n minus 1 plus z to the power of n minus 2 plus dot dot dot, that means this part, plus z plus 1 as a product of linear factors over the set C. It contains 3 marks. Now, if we have the equation z to the power of n equal to 1, we can write this as z to the power of n minus 1 will be equal to 0. Okay? And this equation is having a degree of n, so there will be n number of roots. And what will be there? What will be the roots? One of them will obviously be equal to 1. Next is w, then w squared, and so on. The last one will be w raised to the power of n minus 1. Okay? So, I can write this z to the power of n minus 1 as z to the power of n minus 1 as what do we do? How do we form the quadratic equations, the cubic equations? Suppose we are given that uh, one of the zeros is 3, another is minus 2. Or so how do we frame a quadratic equation or a quadratic expression? Then we do, suppose it is considering all the real numbers, we are not having any complex roots. So it is x minus 3, and there should be a coefficient, maybe a may be equal to 1, a may be some other number, but x minus 3 and x minus minus 2, that is plus 2. So that is how we form the quadratic expression when we are giving two roots. Now it is the nth degree equation and we are given the n roots. So how do we form the nth degree equation? And the coefficient of z to the power of n is 1. Therefore, a will be equal to 1. And we will be taking each of these n roots separately, and we will be writing z minus 1 times z minus w times z minus w squared, and so on, up to z minus w raised to the power of n minus 1. Okay? So the factorization of this expression will be this one. Okay? And they have given the factorization of z to the power of n minus 1 as this. So let us write this equal to z minus 1 and z to the power of n minus 1 plus z to the power of n minus 2 plus dot 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 plus z plus 1 given. Okay. So comparing these two, on comparing the two right hand sides, we get z to the power of, because z minus 1 and z minus 1, this part is common, so z to the power of n minus 1 plus z to the power of n minus 2 plus dot 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 plus z plus 1 equal to z minus w square and dot 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 z minus w to the power of n minus 1. Okay, and this was the answer to subpart I. Fine. So we have got 3 marks. Okay. Express this as a product of linear factors. So these are the linear factor product, means linear factors, and this is the product of the linear factors. And coming to II. Okay. Hence, using the part GI, that is this, and the part F results. The part F results set means like P0, P1. It was 1, P0 was 1. So P0, P1 was the modulus of 1 minus omega. P0, P2 was 1 minus omega square modulus, and so on. Okay. And this was the part F thing. Or otherwise, prove your suggested result to part E. The part E was, this was F. And the part E was, it suggested that, means we had to suggest actually P0, P1 plus, sorry, not, multiplied by P0, P2, then P0, P3, and so on up to P0, Pn minus 1. And we had to suggest the product value, and we had suggested this value to be equal to n. This was the subpart E. Okay. So now, hence using GI, that is this part, and part F results, or otherwise, prove your suggested result to part E. And P0, P1 was this, P0, P2 was this, and so on. Okay. And we have to use, they have said or otherwise also, but it is not a very easy thing. So let us use this. It is better to use this. So I write this. And since we have to have the modulus, so let us take the modulus of both the sides. So from 1, or not 1, rather I'm taking the modulus e to the power of n minus 1 plus e to the power of n minus 2 plus dot 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 plus c plus 1 equal to c minus w, c minus w square, and so on, c minus w to the power of n minus 1 w to the power of n minus 1 modulus. Okay. And since we need 1 minus w, not z minus w, let us substitute 1 for z, because 1 is also a root of z to the power of n equal to 1 equation. Okay, so we can substitute 1 in place of c. It is one of the roots. So taking c equal to 1, we have this is 1 to the power of n minus 1 plus 1 to the power of n minus 2 plus dot 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 plus 1 plus 1, 1, okay, equals, sorry, this is the modulus, not the brackets, okay, equal to, now since these are the products, I can just separate them. So this will be 1 minus w, 1 minus w squared, dot 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 1 minus w to the power of n minus 1. Okay. So now the left hand side, how many ones are we having? 1 raised to anything is 1. Okay. And we are having this is z to the power of 1 and this is z to the power of n minus 1. So there are n minus 1 number of terms between z to the power of 1 and z to the power of n minus 1. And there is this extra one. So we are having n minus 1 number of ones over here from this to this, and there is one extra one. So n number of ones we are having and added together. When n number of ones are added together, what answer do we get? It is equal to n. So this is equal to n. And what is this? This is P0, P1. This one P0, P2. And so on. The last one will be P0, it is not the modulus anymore, sorry. P0, P n minus 1. And this was to be suggested in Sapati. We had suggested the value to be equal to n. It was just a single mark question. And for here, for GII, we have proved this to be equal to n by taking z equal to 1. Okay. So therefore, the part E proved. Okay. So this completes this question number 2. And I'm Nilanjana Sanyal. I'm an online IB Math E, SL and IB Math E HL tutor. And I tutor students from within India and outside India. And I'm starting the small groups for group online tuition for the IB Math E SL students and the IB Math E HL students. So in case you, and these are for the grade 11 students, not for the grade 12 students, because it is too late. I'm not taking any new student from who will be appearing in the board examination in May 2024. Okay. So in case you are interested in joining my group sessions, you are seeing my WhatsApp number getting displayed, you are seeing my email ID getting displayed. You may contact me for more details. Okay. And thank you for staying with me till the end. We meet again very soon. We'll be starting with the November 2021 paper. So paper 1, we'll be starting with paper 1. So till then, bye.